Good morning, or maybe I should say buongiorno. So we are here at DARPA Forward to talk about disruptive technologies. Disruptive technologies that lead to change and even lead to technical surprise. And that's great, but I want to up the stakes a little bit. Because once in a very long while, a technology emerges that is so disruptive, it's so exciting, it's so game-changing, that it can entirely remake how we live. And when such a technology arrives, it can actually define our time in history. So let me give you an example. The steam engine, right, which was the technology that led to and created and powered the industrial age. Or another technology, think of the transistor and the DARPANET, the ARPANET, or the internet. These are the key technologies that created the world of the information age. Now, today, can you imagine a technology that is so disruptive that it could change, well, pretty much everything? How we sense the world, how we communicate, how we compute, how we measure time, how we develop new drugs, how we farm even, everything. So, as I'm sure you've guessed by now, the technology I'm thinking of is called quantum technology. So, good morning again. My name is Mark Rosker. I'm the director of the Microsystems Technology Office at DARPA. And on behalf of DARPA, I'd like to introduce you to the quantum age. Over the next few minutes, we're going to talk about quantum. We're going to try to separate what's real from what's hype. And there certainly has been a lot of hype about quantum, especially recently. It's amazing, right? But will any of the predictions made about quantum really come true? Will quantum technology remake our world? And if so, how? And when? You know, from its creation, DARPA's mission has been to anticipate technical surprise. And it's with this perspective that we look at quantum. What unexpected and revolutionary new capabilities will quantum technology enable? What opportunities will it create? And what threats? Should we be concerned? Some of the questions we'll consider this morning are, what do we actually mean by this word, quantum? What are the disruptive technology opportunities and threats? And especially, what are we at DARPA doing to prepare for this quantum age? Okay, so let's start with a proof. I want to prove to you that at least some of these quantum hype things that you've heard about must be for real. I want to show you an amazing technology. Okay? This technology works by exploiting the nuclei of atoms and their atomic states. It makes these very precise three-dimensional images, even images of the human body in situ. It's magic. It's surgical inspection without the surgery. And there is absolutely no classical, and I mean non-quantum, technology we know of that can do such in situ imaging, not even X-rays. It's a game changer for the medical sciences. Yeah, but hold on. What I'm describing isn't new. As anyone who's been to a doctor can tell you, this is called magnetic resonance imaging, or MRI. And it's been used in the field, I don't know, for maybe 50 years. It's also not DARPA. In fact, the science for this technology came long before DARPA ever existed. Its inventor was Isidore Isaac Rabi. He discovered what's called nuclear magnetic resonance nearly a century ago, and he received the Nobel Prize for it 80 years ago. Or, let's consider this hot, new quantum technology. Yeah, I mean the laser. It's another example of a quantum device. But this one was invented more than 60 years ago. Or maybe a third technology, one that has had a singular impact upon our lives. Yeah, no, I'm not talking about the frozen pizza. Although I admit that's very important too. But what I mean is the magnetron. And this is a technology that is also very old. It was already in wide use by the end of World War II. So when, at the beginning of this talk, I said to you, welcome to the quantum age, my timing was off by a century. Many would say that we already live in the quantum age. So before I go any further, let's take a step back and ask, what do we really mean by quantum? This question inexorably leads us to one human being, and that's Max Planck. Because on this date exactly, on December 14th, 1900, 122 years ago, it was Herr Professor Planck who first presented his postulate, his famous Planck postulate. And that postulate said electromagnetic energy can only be emitted in discrete quantities. Professor Planck told us that the universe, matter, energy, everything, is not continuous as we had thought. It comes in discrete amounts. These amounts are called quanta. So when we say quantum technology, what we are referring to is any device or any approach that exploits the Planck postulate to achieve some characteristics and some performance that would not be otherwise possible with classical physics. And this very moment that I just talked about, right at the dawn of the 20th century, that moment represents the birth of the quantum age. And it's interesting because the development of new physics to exploit new devices to exploit this quantum physics started pretty much immediately. So let's ask the question, if we're already more than a century into the quantum revolution, why all the hype now? And I think to answer that question, we have to think about quantum differently. With all the current hype and hoopla associated with quantum, it helps to break things up a little bit. We'll see that quantum really is three distinct but closely related concepts. Further, that each of these, I'll call them flavors of quantum, is leading to its own new and revolutionary technologies and to its own set of expectations about what more is possible. Today, within each of these three flavors, technology is moving very quickly and leading us to some unexpected new capabilities. So let's start with the simplest case imaginable, and I'm going to call this quantum 1.0. This is the first flavor of quantum to be understood and exploited, and it remains the one that arguably has had the most profound technology impact on our world. Quantum 1.0 technologies exploit the fact that well-defined discrete levels exist in matter, and that these levels can be addressed, they can be measured, they can be exploited. And as we'll see, these offer us new and exquisite technologies, mainly sensing technologies. Okay, so I want you to envision an atom in space. Planck tells us that this atom, maybe it's a cesium atom, it's going to interact with the universe by emitting or absorbing energy in very fixed amounts. That electromagnetic radiation has an exactly known frequency of oscillation. And as technologists, we can use this fact to our advantage. Take, for example, a clock. A clock is just a stable oscillator, maybe a pendulum, for example, and a counter that counts the number of these oscillations. But a classical oscillator, like a pendulum, it's subject to all sorts of imperfections. It might be aging, it might be temperature, it might be external vibrations. And these imperfections change the rate of oscillations a little bit. It's what makes the clock run a little bit too fast or maybe a little bit too slow. But if I replace that pendulum with a cesium atom, that frequency stays nearly perfectly fixed. What I've just described is called an atomic clock. It's a quantum 1.0 device. So one thing we can tell already that quantum does is to provide us with a nearly ideal way to sense and measure time. Okay, so things get even more interesting if we start to poke our quantum system. Quantum 2.0 adds this new dimension, the manipulation and control of quantum levels. For example, suppose we expose our atom to a strong magnetic field. Depending on the relative orientation of the atom and the external field, the magnetic field can break the atomic state into two, a high-energy state and a low-energy state. This is the essential physics for MRI imaging that I talked about a little bit earlier. Okay, so that's quantum 1.0 and 2.0. To get to quantum 3.0, we have to make yet another leap. I guess a quantum leap. Sorry about that. To this point, we focus on the quantum states of particles that are either isolated or perhaps in an electromagnetic field. But groups of quantum atoms can interact with each other. In some situations, the interaction is so important that the quantum state of each particle of the group cannot be described independently of the states of the others, even when you move the particles and separate them, sometimes by large distance. This is called quantum entanglement. It has this incredibly interesting history. Einstein very famously called it spooky action at a distance. But it's real. It forms the basis of quantum 3.0. And as we'll see, this entanglement leads to a number of relatively astonishing technologies, like quantum computing. Okay, so armed now with our framework for understanding quantum, let's consider how quantum is remaking our world. Let's start with quantum 1.0. So far from being new, quantum 1.0 has become so ubiquitous and so familiar, we sometimes seem to forget that it's quantum at all. Most quantum 1.0 technologies relate to sensing the world around us. Its impact has been huge, but much still remains to be done. So I want to consider a few examples. And I'm going to begin with one that, as the director of MTO, is really particularly near and dear to my heart. It's called the transistor. So the quantum nature of the transistor is not so obvious, but it becomes obvious to those who try to optimize transistors. Transistors depend on semiconductors, and a semiconductor is a material with an electronic band gap. But the very existence of this electronic band gap is entirely a quantum effect. Now, transistors have always been important to us and particularly important to DARPA. And DARPA has done a great deal to develop them. So for example, if you think about the cell phone that's in your pocket right now, cell phones became possible 30 years ago because of the development of a technology called gallium arsenide that DARPA sponsored. And it's this gallium arsenide power amplifier component that DARPA helped develop that's still at the heart of cell phones today. DARPA also developed the successor technology called gallium nitride, which is the successor to gallium arsenide. This is a superior technology because the material has a wider quantum band gap. Today, the DARPA DREAM program is exploiting the quantum nature of semiconductors to create even higher power and improved radio frequency transistors. In fact, we've recently demonstrated new records in transistor efficiency. That will mean radio frequency systems that can pass more information and have longer range. In this way, the DREAM program is opening up an entire new world of millimeter wave communications and sensors for everything from automotive radar to the next generation 6G cellular communications that you'll be using. All right, so that's transistors. What else exploits quantum 1.0? Well, we've already talked about clocks and how atoms can be used as oscillators to make these exquisite clocks. So I want to tell you now about a new and very cool quantum clock that DARPA is building. Atomic clocks tend to be very large. They can be the size of a laboratory. But in a program called H6, the quantum oscillators we are exploiting are actually not using atoms, as I spoke about before, but instead they're using molecules. So we believe that this switch can lead to a high-performance clock so small that it could fit in a quarter of a teaspoon. It's hard to overstate how important that would be. Today, both military and commercial systems are massively dependent on the global positioning system to provide time information. That makes us vulnerable to surprise. One way to mitigate this threat would be putting an H6 clock in almost every such military and commercial system. Further mitigation would come from a second DARPA program called Rosker, which is developing transportable clocks with month-long holdover of GPS quality timing. This could enable a secure regional timing source for land or seaborne platforms. Okay, what else? So a third example relates to oscillators. What's an oscillator? These are devices that generate high-fidelity signals at microwave frequencies. That may sound a little esoteric. Why should you care about oscillators? Actually, I would argue for many reasons. In radio frequency communications, again, like your cell phone, how well the oscillator works imposes limits on the signal bandwidth. So if you had a quantum oscillator, it would mean that your next cell phone would capture a lot more data per second. And you will care about that. If you're in the military, a better oscillator will allow you to make a radar that can detect small or slow-moving targets. I want you to think of something like a UAV or a dismount. So the DARPA Griffin program is exploiting quantum 1.0 concepts to realize a nearly ideal radio frequency oscillator. At its heart lies a technology called optical frequency combs, which led to the Nobel Prize in Physics in 2005. Griffin uses a technology called photonic integration to shrink, again, these very large tabletop-sized combs onto a single chip. And that makes them affordable, and that makes them available for key applications. All right, so those are just a few of the quantum 1.0 applications that DARPA is working on. As we move forward, some of the technical challenges we look to try and solve include developing better detectors to measure quantum levels and improving the control of materials and materials composition to change level structures. Okay, so let's move to quantum 2.0. In quantum 1.0, we have seen that just the very fact that states are quantized has led to these new disruptive technologies. In 2.0, when we start to manipulate these states, we'll find some more surprises. So let me start off with a great example, and that comes from something called Rydberg sensors. All right, since the 1800s, radio frequency signals have been measured with an antenna that looks like the one invented by Heinrich Hertz. We're all familiar with it. They're big, they're bulky, and they're especially cumbersome when the signal happens to be at a very low frequency. But for 150 years, if you needed to detect a radio frequency signal, an antenna like this is how you had to do it. It was the only way to do it. So in two programs at DARPA, one called Quantum Apertures and one called Savant, DARPA is exploiting a fundamentally new class of receivers based on quantum physics. These are the Rydberg receivers, and they rely on the quantum state of something called a Rydberg atom. Not only will these Rydberg receivers let you shrink those big antennas into something much smaller, they actually outperform them. They outperform them in sensitivity, they outperform them in bandwidth, and they may outperform them in frequency range as well. So these new receivers may well change everything about how we sense and communicate with radio waves. All right, so a second possibility, a second quantum sensing approach within quantum 2.0 is sensing magnetic fields. So DARPA is developing an entirely new and disruptive way to sense magnetic fields. And this is being done in several different DARPA programs: Ambient, Quiver, and again, the Savant program. All of these are leading the way to this new class of magnetometers that can not just detect a magnetic field with great sensitivity, but can also measure what's called the tensor field. So this helps us locate a magnetic object, its relative orientation, and its strength all at the same time. And knowledge of this tensor field can enable the separation of the Earth's magnetic field from that of the object of interest. That's important, because this ability will make it possible, for example, to map the health of the human brain without all the multi-million dollars of equipment that you need to do it today to make that happen. And by the way, if you're interested to see something like this in action, please attend the ambient program demonstration here at about 4:30. Also, you can see and talk to some of the folks involved and look at the equipment in the lobby, like right near where we checked in. Okay, so some of the key technologies and technical problems that DARPA sees in Quantum 2.0 include things like optimizing sensitivity, finding improved quantum systems, and further reducing size, weight, and power. All right, so that's Quantum 1.0, Quantum 2.0. But let's get back to this intriguing issue, this spooky action at a distance. It's Quantum 3.0 that I would contend is most driving the expectations, the hype, in quantum today. And within Quantum 3.0 technologies, there is no doubt that it is quantum computing that's dominating the conversation. So if you'll forgive me, let's go back to some history. The famous American physicist Richard Feynman was the one who first conceived of a quantum computer, something that was capable of computations unimaginable for a classical computer. And in 1994, the mathematician Peter Shor revealed his famous algorithm that showed you could achieve something like this by, you could factor a huge integer, which is a central aspect of RSA encryption. So from that moment, the hunt has been on, and it remains on, to actually build a quantum computer capable of doing these kinds of calculations. Let me tell you why. For many math problems, like the encryption problem that I talked about a moment ago, complexity grows exponentially with size due to the number of permutations. Classical computers may never be able to address such enormous problems, not in any practical amount of time. But quantum computers can, and only with a small number of qubits. Qubits. That's the name for the logical primitive that underlies a quantum computer. Qubits are to a quantum computer what a transistor is to a classical one. It's a two-state system, and it underpins how computation is actually done. All right, so right now the quantum community is engaged in this huge push to develop systems with more and more qubits. The leading edge today is probably a few hundred qubits, but this number is growing quickly with time. So we ask, does this mean that a useful quantum computer is inevitable? And if so, when? What will its impact be? So at DARPA, we have a program called quantum benchmarking. And in it, we're focusing on two key questions we think have been widely overlooked in the rush to build more and more qubits. And the first one is, how do we know we're getting close to a useful quantum computer? That may sound a bit like a surprising question, but quantum computing could revolutionize any of a growing list of fields. So it's less and less clear where the biggest opportunities lie and when we'll get there. So the quantum benchmarking program seeks to measure progress towards very specific transformational computational challenges. The second question is, can we estimate the hardware-specific resources required to achieve different levels of benchmark performance? By resources, I mean, of course, the number of qubits, but also more. Fault correction, and I'm going to talk about fault correction a little bit more in just a minute. But there's something else before I even go there that I think is very surprising. A quantum computer is expected to heavily depend on a classical computer to do tasks like signal processing and conditioning. What if the classical computer that you need to support all those tasks is too large to build? And I mean ever. So we want to get a good handle on those resources and what will be needed. Okay. At this point, maybe you're starting to get a sense that the enormous opportunities expected to flow from Quantum 3.0 come with enormous technical challenges. Some of them are maintaining coherence and minimizing influence from the environment. engineering scalable systems while ensuring independent control of every quantum subsystem, and developing scalable controls and algorithms. Those are not just hard challenges, DARPA hard challenges. Those may well be insurmountable challenges. I already mentioned one of them, fault correction. Okay, to understand what this means, let's go back to digital computers. It's not really commonly discussed, but digital computers make a lot of mistakes, And there are reasons why these mistakes happen, but they are essentially random hardware faults. Digital computing only became useful and possible when techniques were developed to correct and overcome these errors. That's called fault correction. For quantum computers, how to do fault correction remains an area of research, and really even an area of intense controversy. So at a minimum, fault correction is likely to increase the number of functional qubits required greatly. Fault correction in quantum computers may not be available for a long time. And at DARPA, we're not that patient. So we don't want to wait many years or even decades that people are assuming that it's going to take to realize a full quantum computer. Instead, DARPA's ONSC program aims to exploit quantum information processing before fully fault-tolerant quantum computers are realized. This effort is exploiting hybrid concepts that combine intermediate-sized quantum computers with classical computation. The kinds of problems that ONSC is trying to address with this approach are called optimization problems. Those are very familiar. Some examples are things like scheduling problems, for example, maybe optimizing a country's airline traffic, or resource allocation, like distributing vaccines within a population, or complex decision problems, like selecting stocks in an investment portfolio. So ONSC offers a path to solve many of these important but intractable optimization problems without the need of a full quantum computer. Okay, so I've said now, it might take years to build this full quantum computer. In another program that we call US2QC, we question that assumption that it will take that long in a different way. We ask in US2QC, does there exist a new revolutionary approach that could bring quantum computing into the world faster in just maybe a few years? So here, DARPA is looking to take on the challenge of rigorously evaluating some potentially decades savings shortcuts to making this really big and fault-tolerant quantum computer. If you want to hear more details about some of these quantum computing programs, please come back to the lightning talk here just before noon. Okay, I want to go one step further. The last computing program I want to talk about really is not a quantum program at all. The premise that underlies the QUIC program is that the lessons that we are learning and have been learning in quantum and then in developing benchmarking for quantum algorithms can be applied to classical computing for, once again, these complex optimization problems I was just talking about. The QUIC program, if it's successful, will teach digital computers, like the ones we are familiar with, new tricks. It will force us to rethink some of those limits we thought had applied to classical computation. Okay, so I've asked the question, will quantum define our times? Will it remake how we live? I believe it will. But even a century into the process, I also believe it's still too soon to be sure what the answers are. What I hope to have shown you today is that there are already a great many real examples of disruptive change from quantum across a wide range of applications. And there are many more that DARPA is working to make real. In Quantum 1.0, we saw that the fact that quantum states exist allows for the development of unique solid-state materials and devices, leading to technologies like the transistor. And we can use the quantum states of atoms and molecules for the precise measurement of time. and to achieve breakthrough performance in radio frequency communications and sensors. And though many of these quantum 1.0 technologies have been known and used for a long time, much still remains to be done. DARPA's focus is to improve materials and device performance. Manipulation of quantum states leads to a host of quantum 2.0 opportunities as well. Many of these relate to sensing once again. Some of these opportunities are quite mature, but others are in early development and remain to be tested. Now, recognizing how disruptive they could be, DARPA is heavily engaged in proving and maturing them. Okay, but we need to maintain a degree of healthy skepticism about the claims for quantum, particularly when we consider quantum 3.0, the domain of quantum entanglement. DARPA sees its role here to address some of the most basic questions. How do we know when we're getting close to a useful quantum computer? How can we estimate the hardware-specific resources required? And will resources prohibit us from realizing a useful quantum computer? I focus in this talk about the prospects of enormous promise that entanglement and qubits offer for computation, but they may also present new opportunities for quantum communications and sensing as well. Okay, be it quantum 1.0 or 2.0 or 3.0, DARPA needs your help to continue creating disruptive change. So if you find quantum technologies exciting, work with us. Or even better, come to DARPA as a program manager or as a CETA to help push the quantum community forward. Welcome to the quantum age. I hope you're as excited about it, the possibilities that lie ahead, as I am. May our next century of progress be as exciting and disruptive as the past one has been. Thank you, and I look forward to your questions.
Hello again. So I'll be joining Dr. Rosker on the stage again to help with your questions. Just a reminder, either in person in the audience or online, please submit your questions via the virtual event platform. All right, first question we have. What is the role of enabling classical technologies in maturing the quantum ecosystem, and what role does DARPA play?
Good, that's a great question. So when the transistor, I spoke about this earlier, when the transistor was developed, it's not as if we went straight from a transistor to the information age. There needed to be a great number of things, everything from the support electronics, the silicon itself, the software, all of these things had to be developed, architectures and so forth. And I think much of that is going to be true in the quantum world as well. And so when we think in terms of what is necessary, it will rely on supporting technologies, things like lasers, for example, just to pick one. If you're interested in an atomic clock, or if you're interested in using an atomic receiver, the frequency of your radiation and your choices of materials become critical. So DARPA has a number of programs that are looking at these more classical technologies, but they will have a lot of implications. I'm thinking in particular, for example, of a program called LUMOS, which is sort of moving towards this holy grail of being able to develop lasers that operate at any frequency. That would allow you to use atomic systems of your choice, rather than relying on the happenstance of having an atom which is right at the frequency that you have a laser at. So we need to clearly work across this entire ecosystem in order to realize the promise of the quantum age.
Okay, great, thank you. And then where has DARPA seen investments in quantum technologies lead to successes? I know you talked about some of these programs, some of the things to keep an eye on, but where have they led to successes? And then what did we learn, because we know we like to learn from failure, celebrate it even, from these technologies that did not quite reach maturation?
Okay. Great. It gives me a chance to say something about the history at DARPA of investments in quantum, which go back a number of years. A program called QUIST, another program called Quasar. All these DARPA program managers are challenged to come up with a Q word in their acronym. But QUIST was, if I remember correctly, quantum information science and technology. And it looked at a lot of the fundamental ideas in how quantum systems can be used. It developed the first quantum network, for example. Quasar led to a bunch of sensor applications. Most of what I talked about, the magnetometers, Rydberg sensors, can be traced back to some of those investments. It's too early to say those were great successes and those have yielded. I think we're on the road to seeing that happen. There were other things that were looked at in those sort of early programs that I think have not matured as much. Things like quantum key distribution, quantum radar. So a host of ideas were explored. We're still moving down the road. Maybe at some point we'll go back and revisit those ideas, and maybe there will be the opportunity for further maturation. But I think we've learned a lot in the last 15 or 20 years.
Okay, thank you. Next question, do you foresee quantum-based chips replacing the silicon-based ones for the defense or military applications? And then, two-parter, if the answer is yes, how soon do you think that's going to happen?
Well, that's easy because the answer is no. No, I think what happens with technologies, and I tried to speak about this towards the end, we're probably not going to displace classic technologies, CMOS, silicon. We're going to augment them. And that's true broadly, but when we talk about quantum, I think what we really are speaking about is how can you build more complex systems that can do things beyond what we are capable of doing today. We're not going to give up our chips. We're going to inherit new ones and new capabilities. I guess the when part is, I'm going to skip that. But
you answered it.
Yeah, okay.
Yes. Next one, how closely does DARPA work with industry on quantum challenges?
Oh, extremely closely. DARPA doesn't do anything really on its own. We do things through those wonderful people we call our performers, many of whom are in industry. In the quantum world, there's a healthy number in academia as well. And industry in quantum is a growing, thriving thing. We're very aware of that. Industry here both is startups and also large established companies. There's a lot of research going on. So we're working and monitoring very carefully.
Okay. And then, so along those lines, there's a large commercial investment in quantum sciences. Yeah. So this is sort of the reverse of that question. Yeah. Why is DARPA in this space?
Sure. Yeah, this too is a good question. Why, on the one hand, the interest level has grown so much. I guess it's the flip side of the hype that I was talking about before. The hype, if you want to think of it as such, is the demand part of the equation. But the supply part of the equation is we have a large number of government organizations. We have, as the question relates, a large number of non-government, commercial funding in areas in the quantum space. I think that the DARPA role is not to necessarily be ahead of everyone and to lead this huge community that's forming. It's to look for unusual opportunities that are not being explored. So I give an example or two. The US2 QC program is one where we are very consciously trying to look at ideas that the commercial world and maybe even other government organizations are not looking at. That's what DARPA does.
Okay, great. And then while scaling may be addressed by employing molecular computation as opposed to singular atomic, and sorry, I think there's something missing in this question. Does the temperature sensitivity of quantum clocking get addressed in scalability? I think.
Yeah, I'm trying to understand the question too.
I think there's.
Yeah, okay. So I think what they're saying is we move from an atom to a molecule, and how does that help, right? And how does that relate to things like temperature sensitivity? Actually, it turns out that again, we believe, this has not been demonstrated yet, but we believe there are potential advantages because atomic states tend to be very high temperature, where molecular states can be much lower in temperature. So that gives you some advantages. And when I talked before about potentially making very small teaspoon-size clocks, in large part, it's these thermal advantages that end up being the thing that drives size.
Okay, great. So you talked about this a little bit, actually, in your talk with quantum research coming from all across DARPA in different offices. So this question is, we don't have a quantum office. How do you decide, as an agency, how do we decide which office those programs will reside in?
Yeah. So you're right. There is no quantum office at DARPA. You might argue that every office is a quantum office. I think it's a competition of ideas, and different offices have different skills and different skill sets. Most of what's going on right now relative to quantum at DARPA resides in either the Defense Sciences Office or my own office, the Microsystems Technology Office, but it's a competition for good ideas. And so I think we're interested in developing those as they occur.
Okay. You talked about this a little bit too, but
Yeah.
maybe more in depth and more, I guess, maybe looking for more guidance. But what materials might be required for quantum computing?
Well, I talked about this to a degree, but if there's any one thing that is really driving quantum from a material standpoint, it is that we are looking for coherence, right? For things that materials that do not dephase. So most of the materials issues are really focused on those kinds of improvements. But that's just the leading edge. That might be asking for, analogous to asking for the better gate in a transistor. You have to build everything around that transistor as well. And all of those, each of those issues, how you do the interconnects, how you do the fault correction, those are all going to rely almost certainly on some critical materials requirements and new materials.
Okay. So this next question is a little more wide open than I think I'm going to let it be. So the question is, if you could get any DARPA program approved tomorrow, what would it be and why? But since we're talking about quantum technology, I think I'm going to add the word quantum program in there.
No. I think this one is from my staff. That's a really interesting question, and one that I'd like to think about rather than jumping to. The entire point of being at DARPA is that we're always looking for the next good idea. I guess I could say if I knew the answer to this question, we would be proposing this program at Tech Council tomorrow. In a sense, we are working on a bunch of different ideas, and I don't want to give too much away. So I'll punt on that one.
Okay, fair. And maybe someone else here can make a recommendation.
Oh, I'm sure they can.
Guaranteed. So what do you see as the role of DARPA technology in the medical industry? You shared a little bit in your talk about how it's been used, but how do you see it going forward?
Yeah, again, from the context of quantum, right?
Mm-hmm. Correct, yes.
Yeah, so, sensing things in the human body, right? I gave the example of MRI. I mean, clearly MRI is not new. I'm not suggesting that it is. But the thing that can be new is the ability to sense magnetic fields, and I talked about that. That's what ambient is trying to do. That could really be game-changing. I think the demonstration that you'll see out front is one where, again, using magnetic fields, one is capable to remotely measure heartbeats. It's hard to imagine the number of potential applications that result just from the sensing opportunities alone. And I think I'm being a little small-minded by limiting myself just to sensing. So I think they will be large, but go talk to BTO and beat them up about that, please.
All right, so a biological technologies office and microsystems technology office.
our friends.
Combination, yes.
That's right.
And they are friends, indeed. What is DARPA doing with international collaborators in quantum, speaking of friends? There is a lot of work going on in other countries. How is DARPA leveraging that work?
Yeah, some of the programs that I talked about, things like QUIST from years back, had international aspects associated with them. I hope I didn't suggest that all of the good work in quantum is going on in this country. That's definitely not true. There's an enormous international effort, and in terms of the total investment, I'm sure it's larger in aggregate overseas than in the U.S. So we're very aware of that. Our programs include foreign companies and foreign universities as appropriate. And we are very much tracking to see what happens and working with foreign entities to watch progress in the field.
Okay, thank you very much.
Thank you, and thank you for letting me spend the time.